Well, hello. My name is David Adrian. I am coming here from Google to talk about Chrome's root store. I work on the Chrome security team there. I am a product manager, but please don't hold that against me. So in the Chrome 105 release notes, which I'm sure you've all read, you might have noticed that we said that Chrome now maintains its own default root store and built-in certificate verifier, which raises the question of what was Chrome doing before then? And so I'm here today to try and explain a little bit about what that actually means, why that's kind of a change in policy from what we were doing before, and try and make you kind of care about the Web PKI and the problems in the Web PKI that go kind of beyond just core cryptography. So Chrome is a web browser, right? And we want the web to be great. People do lots of things on the web. They learn things. They meet people. They fall in love. They spend money. Very Google of me to end with spend money. But for all of this to work, the web needs kind of this baseline of security, this idea that when you're talking to a website, the only people who can see what you send to the site and what the site sends to you is just you and the site. And we get that from HTTPS. Cryptography is like the only area of security that we're kind of actually good at, where we have provable guarantees about the security of the system. And cryptography gives us the tools to take an insecure channel and then bootstrap it into a secure channel. And that's really incredible. It's what enables HTTPS and kind of what enables the baseline of security on the web. And what I mean by secure channel is three properties. The first two we kind of get out of cryptography for more or less free. Kind of confidentiality and integrity. If you have a halfway decent cipher, that's just the core properties that you get from encryption, the idea that people can't read what you're sending and people can't modify it. The third property, however, is where we kind of go past just cryptography and we start venturing into the real world. Authentication. How do you know that you're talking to the right person? On the web, what this means is when you type in a URL, how do you know that the content that you're getting is actually from that URL? So I'm not talking about phishing. I'm not talking about getting tricked into typing in G00G or something like that. Why does the URL actually what you're seeing? I've used these XKCD characters in slides for years at this point, and now Randall's here at the same conference, and I feel very self-conscious about it. So cryptography gives us a tool to kind of deal with this. It's called digital signatures. They enable us to authenticate someone if we know their public key. A quick refresher on kind of the API of signatures. We're not going to go into any of the math. It's basically we have a key generation function that returns a key containing a public and private component. We can sign data using the private key. So you've taken the private key and some data in a sign, and you output a signature. And then anyone can use the public key. The public key you can distribute to people. The private key you keep secret. Anyone can run the verify function, which takes the signature and the public key and the data that was signed and says, hey, was this actually signed by the corresponding private key? It gives you a Boolean. So the idea is that the only people that can generate the valid signature is the person with the private key. And so this kind of solves authentication for us, but it gives us this other problem, which is okay, if I know someone's public key, I can authenticate them, but how do I know where their public key is coming from? Within the internet, this is where certificates come in. So a certificate, in kind of its most simplest form, is basically a signature over three things. It's a signature over the name of the site, the URL, the public key of the site, and then the name of the issuer, the person that issued the certificate. And then it contains a signature from the issuer over that whole body. So looking at an example on the web, if you're trying to connect to wikipedia.org, you would get a certificate from them. This is assuming you're over HTTPS. You would get a certificate that says wikipedia.org. It would have their public key in it. The issuer name would be Let's Encrypt, which is a CA that you've probably heard of, and then a signature from Let's Encrypt's key over that body. And then, as long as you have Let's Encrypt's public key and you trust them, now you can be oh, this is where Wikipedia's public key comes from. But this raises yet another question of, okay, well, where did the issuers come from? We started with who are you, then we said, okay, well, where does your public key come from? And now we have where are these issuers coming from? And the answer is browsers and platform vendors make them up. They pick the ones that they like. So basically, vendors trust a set of certification authorities to validate domain ownership and then issue these certificates that say, hey, this key is associated with a set of names. And this set of certification authorities is represented by a set of root certificates, certificates basically signed by themselves, corresponding with the CAs, called a root store. So browsers and platform vendors maintain these root stores, and then if they have like policies and requirements around kind of what is included in these root stores, that's usually known as a root program. So back in the 90s, like there was no root program, there was just like a collection of files in Netscape. Nowadays, there's kind of a few major root programs. Mozilla runs one, Apple runs one, Microsoft, and Chrome, as of about a year ago, actually runs its own root store. So let's go back and look at how this works on the web and how this kind of provides security. So if Wikipedia has some key here, represented in green, associated with their name, they go and get their key in a certificate signed by Let's Encrypt. So Let's Encrypt is represented by the red key, and then their signature is the red pen. So the first thing to note here is that like signatures are actually edges in this graph. They're not nodes. And so then Let's Encrypt has its key, and then they have their root certificate, the red key signed by itself. That's included in most modern root stores. However, Let's Encrypt's a fairly new certificate authority, and so to kind of bootstrap when they got started, they got cross-signed by a different older CA known as Trust, which is present in many older root stores. And so that's their red key signed by the yellow, and then the yellow key signed by yellow exists in many older root stores. And then browsers are responsible for kind of building these chains, walking this graph. And if they can take the certificate that belongs to wikipedia.org and they can find a valid path back to their root store, then they say, okay, this certificate is trusted. That's what certificate verification is. And this whole system of certification authorities, browsers, root stores, sites, keys, and stuff is known as the Web PKI. Within the Web PKI, CAs are responsible for a few things. They're responsible for domain validation, meaning ensuring that the requester of a certificate or a subscriber in Web PKI parlance actually operates the domain. They're responsible for then like actually issuing the certificates and then conveying status of those certificates, meaning like is the specific certificate revoked. And this means they're very important because a single compromised CA could negatively impact any number of domains on the internet. What I mean by that is that if a CA issues a certificate to someone who doesn't actually control the domain, they can impersonate that domain. And so even though Wikipedia usually, gets their certificates from Let's Encrypt, if super sketchy CA LLC issues a certificate to an attacker that says they're wikipedia.org, kind of doesn't matter that they normally use Let's Encrypt because that malicious certificate could still be used to impersonate Wikipedia. And this could, in theory, a compromised CA could impersonate basically any site on the internet. And so really, like we started with cryptography a little bit, but what we've ended up here is a bunch of like human problems about trust. Of like, who are these CAs that we're trusting? Are they doing the right job? Do we trust the browsers to actually implement this verification algorithm correctly? Things like that. And what I'm kind of talking about today is steps we're taking in the Chrome root program to kind of reduce some of the human element and try and make the system more secure. And the security of the system is actually very important because like nearly every page load is over HTTPS these days, much more than it was 5-10 years ago. And so this system is, the security of the Web PKI is kind of fundamental to the security of the entire web. So I'm going to pivot for a moment and talk about Chrome. So Chrome launched in 2008. At the time, it used the platform-provided root stores. In fact, it only launched on Windows, so it used way more than just like the Windows root store. It used the Windows HTTP library, it used the Windows TLS library. The processes were inter-process communication was basically just passing HWINs all around. It was, it was a new web browser, so it relied on the kind of underlying platform APIs a lot. But over time, Chrome adds, more platforms and so on, and runs on more devices. And browsers basically are offering a set of capabilities to websites And they need to do this consistently on a diverse set of devices. And so, as you might expect, like the browsers kind of start eventually providing their own implementations for things because, did I just lose my mic? No, okay. Browsers start providing their own implementations for things to better control the performance properties, to better control the patch rate, right? Like a browser probably updates at a different rate than the user actually updates their underlying platform. Browsers really care about like web technologies. Not to say that like underlying platforms don't, but they have a lot of other considerations. Their focus is not on just the web technologies. And so browsers are incentivized to kind of make them faster and prioritize work on them much more than like an operating system might be. And so you kind of see more and more things get in-housed into browsers. So looking at the kind of platform certificate verifiers, the code that's responsible for building those trust chains, like Chrome uses them. It's a good thing to kind of use them, be a good citizen of the platform. You get benefits like automatically picking up configuration changes and locally installed root certificates. If you're an enterprise, you probably need root certificates that authenticate like your private intranet sites or sites on your local network. So by using the platform verifiers, you usually just kind of get that for free. But it has, all of the limitations that I just mentioned for like why browsers want to in-house various implementations. And specifically for cert verifiers, it might not meet the needs of a browser that needs to handle trust incidents on behalf of its users. So what do I mean by trust incidents? Well, this is when things go wrong with a CA. Here's a sampling of a few of them. The big one was in 2011 when a Dutch certification authority called DigiNotar was compromised and used to issue rogue certificates, including for Google properties. They were distrusted almost immediately. Similarly, in 2011, there's a different CA that accidentally was issuing other CA certificates to sites instead of like end entity certificates. And then one of those was used to issue rogue certs for various websites, including Google. Slightly different vein, WoSign and StartCom back in 2015, 2016 timeframe. They were backdating certificates to avoid increased security requirements. Specifically, SHA-1 had been kind of deprecated and banned for certs newer than a certain age, and WoSign was issuing certs that said they were from before the cutoffs to get around the requirement. And then similarly, like Symantec out in 2017 had kind of repeated failure to validate domain ownership for issuance. And they were, ultimately distrusted by Chrome. And so when these things happen, right, like browsers still have kind of this obligation to secure their users. But if you're using the underlying platform certificate verifier, it might not, be as up to date as the browser, or just, the operating system is probably not moving their root store as fast as a browser might want to. And so you kind of have to layer extra checks onto the platform verifier. So in this example, the client connects to some site which presents a certificate. Chrome has its own TLS library, but when we were using the platform cert verifiers, we take the cert out of the connection, we'd pass it to this cert verifier, which would give us back like yes or no, and then maybe the chain that it found for trust. Then we would look at that and we would say, hey, does this like chain up to WoSign or one of these other CAs that we blocked that the platform might not have blocked yet, or that maybe you weren't on a most up-to-date version of the platform and so on. And if it was, we would say no. The problem is sometimes there can be more than one chain, right? So in this example here, there's a cross sign of the green CA by both the red and the yellow one. And so if we didn't like the red one, but we were okay with the yellow one, but the platform only told us about the red one, like we have a false positive certificate error here because we've rejected the connection, but there is another valid trust chain. So, I mean, this has been the case for many years, but we'd known it was a problem. And so ultimately, we decided we wanted to run our own root program and run our own cert verifier to kind of have consistency on these failure cases, right? With the platform verifiers, unfortunately, are inconsistent in the case where it kind of matters the most, which is in like distrust in the failure cases and the edge cases. And so this way, if a certificate verifies on Chrome on Windows, it'll verify on Chrome on Mac and Chrome on everything except iOS for Apple platform reasons. And so in conjunction with our own verifier, we shipped our own root store, and we can update it with Chrome and kind of address all of those concerns. And then the Chrome root program, which is like our set of policies around the root store, it can more directly represent Chrome in the Web PKI, which I'll get into in a little bit. But first, I want to talk a little bit about how you actually launch this, right? Like, Chrome had been around for 13 or so years around the time that we did this. It's got like a lot of users. And so what did we want to do when we were actually launching our own verifier? Well, we wanted to have like a high bar for cert verification, do it right, kind of push the bar on like what, like you actually encoded your certificates to like the RFC standards and things like that. But we also didn't want to break things. And for compatibility reasons, like the main concern was we had to be able to import these local trust configuration changes, so local roots, all that kind of stuff. So we did a stage rollout platform by platform with enterprise policies and flags to revert to the old behavior for people that needed that. We launched platform by platform, learned some interesting things in the process. Windows has 13 unique locations for trust and distrust information that we import from. The kind of craziest of which is a special store called the Trusted People Store, where certificates need to be treated differently when they come from there. On Mac, we load trust anchors from the default and system keychains, but if you ask keychain for cert information too often, it tends to become non-responsive, and then your browser like hangs, it turned out. So we had to cache that at startup and query it occasionally to make it work. Otherwise, we did something impressive, which was actually decrease the active users in Chrome if you were in this rollout, because your browser would become non-responsive. On Android, there's an API in the Android SDK to get kind of custom root certs out. So you just have a nice like cross-language Java to C++ callback synchronization problem, which we all know is very straightforward. And then the good thing about Linux and Chrome OS is, since they really all just kind of use Mozilla's root store and shove it in etc NSS, we'd actually been able to use our own verifier since about 2019. So then updating to use our own root store was pretty uneventful. How did we actually validate that this was like working and know that this stuff was happening? Well, we did two things. We ran a dual verifier trial on a subset of users that ran both the platform verifier and our verifier, and compared the results. And then we looked for differences and said, you know, do we expect these? Then we also did like standard A/B test of like CCV versus the platform verifiers. And we learned some crazy stuff, which is that despite the fact we launched a stricter requirements, we actually decreased certificate errors across the board. We did a few things. So it turned out our verifier was more accurate. The main platform for this was Windows, 40% decrease in cert errors. And the reason for this is older Windows didn't have their root store updated. And so they were actually missing Let's Encrypt's root. And that yellow root that I diagrammed earlier from IdenTrust had expired. And so there was a chunk of sites that were like unable to verify, or a chunk of users that were unable to verify Let's Encrypt sites and users. And after we shipped our own root store that updated, you know, out of band of Windows, we had more accurate verification. Similarly, not doing like kernel calls speeds everything up. So certs verify faster. This results to faster page loads. We had about a 1% decrease in time to first contentful paint across all of Chrome after we launched the cert verifier. And then Google maintains a set of metrics known as the core web vitals and kind of a pass-fail threshold for them, saying like if your site loads and I think it's under 300 milliseconds, you like pass core web vitals. And so because we did cert verifier faster, we had a 0.1% increase in pass rates for core web vitals, all from a root store. So the thing that I've kind of skipped is like, okay, so we launched our own verifier, but we could have just like cribbed Mozilla's root store and shipped that with Chrome. Like, why did we do our own root store and root program? And the answer to this is basically like the verifier and the root store kind of improved security, improved experience, all those metrics that I just mentioned. But really we wanted to like take a more active role in improving the Web PKI in general. And to understand how we do this, I want to talk about CAs, but I'll also note that like we've posted all of this online publicly in a document called Moving Forward Together, and the kind of TLDR of it is that the Chrome root program is looking to increase the security of the Web PKI through agility and simplicity, and that the main knob that we have for this is automation. And all of those words are just like objectively good things, and so like it doesn't mean a lot to just say I want more security and things to be more agile. Like we've all tried to use Jira, right? And so to understand like what that means and why that's good and how we hope that plays out, let's look into how you actually operate a CA. So if you want to become a CA, kind of divide it into two parts, bootstrapping and then your actual operations. If you're starting a new CA, you basically need to generate some key material on an HSM, and then from that key material, you can generate your root certificate, your PKI hierarchy, all that fun stuff. You have to comply with a set of rules defined called the baseline requirements. These come from an organization known as the CA Browser Forum, which is a standardization body that says like how CAs have to behave. You can think of them as defining the content of certificates, whereas RFC 5280 defines kind of the structure of certificates. And then once you've done that, you have to apply to root programs. You show them your audit report and say, look, I'm complying with all of these rules. Here's how the key was generated, and so on. The main downside here is that the CA's trustworthiness is assessed by like paperwork-like audits. You might be thinking about these audits as like something that like NCC Group or Trail of Bits does. It's not that kind of audit. It's like a financial thing, basically. CA chooses the auditor. The audit outputs like 2 to 3 pages of boilerplate. The quality varies. Sometimes the audit organizations aren't actually accredited and kind of disappear from the world, a thing that happened like last November with a group called the Princeton Audit Group. So this is really about like compliance and not security. Once you are actually a CA, though, then, like I said earlier, you have 3 things to do: domain validation, issuance, and certificate status. So how does domain validation work? Well, the base idea of how we verify that like a subscriber actually controls the domain that they're requesting a certificate for is by the CA sending them some sort of challenge and them sending it back. For many years, the main way that we did this was like email, and that's still allowed, as is like validating over fax. Let's Encrypt kind of standardized a automated protocol. Some CAs had stuff like this internally, but Let's Encrypt was the first to kind of standardize an automated protocol known as ACME that basically does this challenge response out of band type process. There's various ways of doing it, like posting files in .well-known, editing specific DNS records, changing specific content in a TLS handshake, validate domains, and then you can like automate issuance of certificates. And this is really good, and we want to see more of it, because automation kind of reduces the risk of a certificate, because it lets you get certificates faster and change things faster, and that reduces risk. Why does this reduce risk? Well, when you validate a domain as a CA, that validation can actually last 398 days currently. So if you were getting like 90-day certificates, technically you wouldn't have to, if you were issuing those as a CA, you technically wouldn't need to revalidate domain ownership until day 398. So you can see here that you could issue like 5 different certificates off the same validation. Now, like, what if the world has changed in between when you validated that domain and when you issued the certificate? It actually could be even worse, because it's like 398 days, and that's the max length of a certificate. On the 397th day of a 398-day certificate, you could reuse the same domain validation, issue another one, and have like almost 800 days worth of certificates off of a single domain validation. And all of this kind of represents risk. Like, a domain validation is effectively a point-in-time validation spread across the lifetime of a certificate. So the longer that a certificate lasts, and the longer that you can reuse domain validation, is basically increasing your risk window, because something might have changed between the validation and when you then and now, right? Like in an ideal world, we would somehow be able to validate domain ownership on every connection, but that's not really feasible, because it's done out of band. And so the Chrome root program is working to encourage automation so that we can eventually reduce or eliminate domain validation reuse, and ideally eventually reduce the maximum certificate lifetime, which is currently 398 days, down to something lower. You might have also noticed that when I was describing domain validation, I described more network connections, which means that they're at risk of kind of PGP hacking, DNS spoofing, all that kind of stuff. And that could result in misissued or maliciously issued certificates, kind of through no fault of the CA, right, if you just have a sufficiently powerful attacker. The reality of this situation is like we're never really going to fully get rid of it. The Web PKI is really just like a distributed and delegated system for trust on first use to CAs. But we can still make it better. And one way that we can do that we're working to pass a ballot in the CA Browser Forum, is to require domain validation from multiple perspectives. Various CAs like GTS and Let's Encrypt already do this. But this, drastically reduces the risk of kind of like certain DNS spoofing and BGP hijacks in order to achieve a malicious certificate. On the issuance side, there's kind of one main security question after you've validated the domain, which is basically, how in the world would a site operator know what certificates actually exist for their site, right? I mentioned that there's this rogue certificate from DigiNotar back in 2011. Like, the only reason at the time that Google knew about that was because like users reported it. And so this is a bit older, but in addition to kind of the baseline requirements, and RFC 5280, root programs might add some of their own requirements on top of that. And so Chrome, both the Chrome root program and the Apple root program, require that CAs participate in certificate transparency, which is a system for revealing targeted attacks like the DigiNotar one by requiring trusted certificates to be publicly logged in these things called certificate transparency logs. And then additionally, like, you can audit then certificates for compliance with the rules, things like that. This is how like the SHA-1 issues and stuff were caught back in 2015 and so on. In the certificate status space, well, that's basically all about revocation. And like, revocation is the idea of revoking a certificate if the key in it was compromised. So if you, for some reason, posted your private key on Pastebin, you probably want to like revoke the certificate that it was used in. That seems pretty straightforward, right? Well, we have two mechanisms for this. The first one is called certificate revocation lists, or CRLs. These are basically big lists of certificates that have been revoked, and they're per CA. And there's a whole host of reasons you might want to revoke. There's key compromise, like I just mentioned. You might revoke for administrative reasons. Maybe you sold your domain or just got rid of it, and so you want to revoke the certificates for it and then let the new owner have certificates, right? So some of these are kind of scary. Some of these are kind of more administrative. But CRLs have a few problems, which is that they're really too big for clients to download. There are tens or hundreds of megabytes of revocation data kind of updated daily. They're expensive to host. After Heartbleed, a bunch of certificates were all revoked all at once, and it costs $400K to $1 million a month if you were paying at AWS rates to host Global Sign CRL after Heartbleed. And they're not really required. CRLs were actually optional in the BRs. In fact, because they're so expensive, before Let's Encrypt, there was a CA called StartCom, and they issued free certificates that you could validate over email, but the one thing that they charged for was revocation, which is kind of like, seems silly, but it's where the cost was. It was $20 to revoke a certificate, so don't screw it up. The online certificate status protocol is the other way of doing revocation, and basically this is just an RPC for asking a CA, hey, is this specific certificate revoked? So if you like wanted to use this on every connection, you would open your TLS connection when you got to the point where you got a certificate. You would then go to the CA and say, hey, is this certificate revoked or not? They would say yes or no, and if it's fine, you would continue your connection. This also has a ton of problems. For one, it's a privacy leak. It reveals browsing habits to the CA, which you probably don't want to do if you're like checking it on every connection. It's effectively, it's too slow and unreliable to be fail closed, so it has to be fail open. Once it's fail open, you kind of ask, like, why do we even check this? So browsers didn't check it either at all or most of the time, unless you like enabled weird specific settings for it, which some like larger organizations did. But like CAs were still required to do this, and then there were incidents around like, are they doing this correctly? Yet no one's actually looking at these, so why does it matter if they're doing this correctly or not? And it's expensive. Let's Encrypt said on the CA browser for a mailing list, they receive more OCSP requests than they do for all of their Acme endpoints by an order of magnitude. And for what? Like, where are these coming from? So a better approach is to kind of simplify all of this. So step one, let's just get rid of OCSP, right? Like, why are we wasting time enforcing requirements that don't add security value? Let's just make it optional. Like, if some people really want it, that's fine, but like browsers aren't using it, so why are we requiring it? About 1/3 of all incidents disclosed to CCADB were to do with OCSP, and effectively had no security impact. Okay, so then let's mandate CRLs. Browsers can distribute revocation information consumed from crawling these CRLs if all CAs have them, and then can build kind of custom mechanisms for getting at least some of the revocation information to clients within some time window. It's never going to be all that fast, but there's been improvements in this space, cascading Bloom filters, all that kind of stuff. Mozilla is really kind of pushing forward here with a project called CRL Lite. And we're looking at them very closely. And then final step is like, let's reduce the need for revocation in the first place by reducing certificate lifetimes. So again, like this is why we're so big about automation, because automation is really what unlocks short-lived certs. If the lifetime of your certificate is shorter than the window in which the browser could distribute revocation, even in an ideal world, right? Like you don't really need revocation anymore. So we actually did this recently. We wrote and passed a ballot in the CA browser forum that called Make OCSP Optional, Require CRLs, and Incentivize Automation. And the way that we incentivized automation was by saying, hey, we're going to define these short-lived certificates as certs with a 10-day or less lifetime for now. And if you, a CA, issue a short-lived certificate, not only do you not have to do OCSP, which is optional, you also don't even have to put it in the CRL. Like you don't need to track revocation status at all. And you know, as any software engineer knows, doing less work is just way easier than doing more work, right? So kind of going back to the moving forward together slide, which just listed a bunch of good things about like security and simplicity and agility, like that is actually what we're doing though. Like we're trying to make the system simpler. The main tool that we have for this is by leveraging automation to kind of add agility to the PKI to make it easier to issue certificates, make them look shorter, make it easier to change between CAs, all of these things. And that ultimately we think that by doing that, that will make the web more secure. And it's kind of very paramount that we actually do have agility within the Web PKI because there's some big changes coming up that require agility, specifically like if we migrate towards post-quantum secure cryptography, like everybody is going to need to change. We're probably going not only needing to change our software, but we may need to change some of the like entire systems that we use because of the size of this cryptography. So agility really is important to keeping the Web PKI secure in the long term. So why does Chrome have a root program? Well, we're trying to improve security by responding to trust incidents better. We improve the experience because now Chrome loads pages faster. And really, we're trying to improve the Web PKI by kind of taking a more direct role on behalf of Chrome users to both respond to incidents and make the PKI better going forward. If you're interested in this stuff, there's a public mailing list called public@ccadb.org that you can just join. And that is where CAs submit requests to kind of join root programs. There's discussions about the various CAs. This is a collaboration between Mozilla and Apple and Microsoft and Google. The prior kind of iteration of this was, perhaps you've heard of the MDSP, Mozilla DevSec Security Policy mailing list. This is basically kind of a browser-neutral version of that. And so if you're interested, like you can join and kind of keep track there. It's free. The CA browser forum is unfortunately paid, but it is what it is. And so, didn't Chrome already have a root store? Sort of. Once again, my name is David, and I guess I have a time for a couple of questions. Thank you. So the question was about OCSP stapling and whether it was like a failed idea. So making OCSP optional doesn't get rid of OCSP stapling, which is the idea of taking an OCSP response and the web server basically asks for it in advance and then attaches it to every TLS handshake to prove that the cert's not revoked. The issues with it are basically that web servers are really bad at doing this. OCSP servers are bad at being up. And I say that kind of jokingly, but also like you don't really want to put, if you are running like a site that where uptime kind of correlates with money, you really don't want to have a dependency on like a random third party in order to open TLS connections. And so lots of people didn't really want to use OCSP stapling. And then it was difficult to kind of indicate when OCSP stapling was required. Like, should I be checking for this certificate or not? Like, if you don't staple, is that bad? Is that good? Again, you kind of got into this like fail open situation. So it's certainly suitable in some contexts, but it's not really a solution for like the general public internet.
How much of this, you talk about Chrome a lot, but how much of this also applies to Chromium and people that have used that as their internal browser?
Yeah, so the Chrome root store ships by default within the Chromium. Like if you just do a Chromium build, a non-branded build, you will get the Chrome root store. But I think it will be described as the Chromium root store somewhere in settings, like the string does change. So downstream projects, I believe, have mostly adopted this, right? They're certainly capable of changing it, right? Like various enterprise browsers might want to add or remove things at a different rate. I believe Brave uses the Chrome root store at this point. I know they were the kind of the first Chromium embedder to have a CT policy. So like basically every downstream Chromium project can leverage the Chrome root store or say, screw it, I don't want it, and do something else.
So you maybe answered this, I missed it. Because Google maintained an Android platform root store, and now there's a Chrome one. Is Google maintaining two root programs, or are they merged?
Google does, there is a Android root store that is separate from the Chrome root store that is kind of used when you are using non-browser apps on Android. And then users can modify. They mostly track the Chrome root store in practice, though.
I know you'd made the joke about OSCP replies being up. Obviously, issuing CAs also issuing certs also requires uptime. Mm-hmm. Do you have an opinion on a good balance for where we're going with the short-lived lifespan? I assume, for instance, 10 minutes would be too short. So what's the golden place we're shooting for?
In practice, in the current system, there's not really like anything better than 24 hours. There's no reason to do that. I think like we posted a document saying like we would like to eventually bring 398 days down to 90, right? And like in general, every kind of certificate lifetime reduction, we went from basically infinite to like 1,200 days to 900 days to like 398. It takes like 3 to 5 years every time someone is like, we want to reduce lifetimes. Various people have various opinions on it, right? If you're doing manual certificate issuance, like if you work somewhere and you have to manually like get a new cert and update it, right? Like you really don't want shorter lifetimes. And that's some of the feedback we heard when we first started talking about 90 days was like, if you guys require 90 days, like my job is just going to be only updating certificates. And you know, I certainly, that's why we're pushing automation so much.
Thank you.
Hi, I was wondering how we should handle test certificates. I guess my experience, I've been using a test CA, and we put that into the Windows Store, and it seems like Chrome still picks it up. So.
Yep. Yeah, so that's why we spent all that time doing platform integration, is so that when you add like custom CAs for tests or anything else, Chrome should still automatically pick them up, and if they're not, it's probably either a bug or because the certificate is malformed. And then we're working on some better facilities to do that directly in Chrome, as well as like somewhere to expose like what we imported, what we didn't, and why, beyond just like the Chrome netlog. So to make that a little easier. I think we have time for maybe one more question.
10 days is a long time to go without a CRL. Like if you leak your key, you have to wait 10 days if you did it right after issuance. Mm-hmm. Am I interpreting that incorrectly, or?
Yeah, that is certainly a long time, but like in practice right now, that time is actually infinite because there's like no good way of doing revocation. So 10 days is where we're at now. That's also the cache period for OCSP. So if we were doing OCSP stapling or had a reliable way or like wanted to fail closed on OCSP, both the CAs and browsers, I don't remember if it's 10 or 14 days, it's somewhere around there, you could just cache that response for like 2 weeks. So even if we were checking that on every connection, that's like the time range we would be looking at for revocation anyway. And so that's a little bit with like where the short-lived cert lifetime came from, was like, well, even if you were checking revocation, you couldn't do better than 2 weeks right now, so let's do 10 days.
Cool, thanks.
All right, well, thank you.